In this video, we're going to talk about infinite limits. So let's start off with an example. So let's say I have this function here, f of x. It's a rational function because I have a variable in the denominator, and I can now figure out what is going to break my domain or be a restriction on the domain. So if I plugged in 2 for x, that's going to give me 0 in the denominator, and we know that that just will not work. So that's going to create a vertical asymptote right here at x equals 2. Now if I talk about the limit as x approaches 2 of this function, coming in from the left, which is modeled here, remember that little negative in the exponent spot? So if I'm coming in from the left, it looks like that thing is going to go towards negative infinity because that asymptote is going to prevent it from touching x equals 2, but it'll get really, really close and it will go to negative infinity. So that limit isn't going to approach a certain number, but instead the idea of negative infinity. And if I'm coming in from the right, so it's over here, which is modeled by that plus, if I'm coming in from the right, it's going to go to positive infinity. So remember, this is modeling it graphically, and then I can also do that numerically by making a table of values as I come in from the left towards x equals 2, and coming in from the right, I notice that coming in from the left, my numbers get crazy negative, really big and really negative, and then coming in from the right, the opposite is true. So it starts really small and positive and it gets really big and positive as we approach x equals 2. And something else to note in this example is that I can have two different limits. I can have a left-hand limit and a right-hand limit. But since this equals negative infinity and that equals positive infinity, I can't say that the limit as x approaches just 2 will exist. And here's the formal definition of an infinite limit. There's a lot of math jargon here, but essentially if you did what we just did in that example and you check to see at some number c what's happening with that graph, especially if there's an asymptote, if it's going towards positive or even negative infinity, you can describe a limit just like we did in that last example with a left hand or a right hand. But something that's really important to note, as we talked about in that last example, that if you see a limit that approaches positive or negative infinity, it doesn't mean that limit exists. It actually means that it fails to exist because it approaches like really big or really small numbers. So let's put that definition to work. So let's look at this example here. I've got another rational function, the variable in the denominator, and x equals 1 is going to be a vertical asymptote because it's going to zero out our denominator. So that means that as I approach 1, x equals 1, from the left, it looks like it's going to positive infinity. Same thing on the right, it's going to go up to positive infinity. So that means that the limit as x approaches 1 is going to be infinity. And now for this example, it was like the first one we looked at where I have these two pieces here. So this is also a rational function. Vertical asymptote is going to be at x equals 1 because that's going to zero out our denominator. So as the limit approaches 1 from the left, it goes to positive infinity, but as it approaches from the right, x equals 1, it's going to be negative infinity. Here's just a quick reminder about vertical asymptotes. Here's the definition and what you do with a vertical asymptote. So it's essentially if you have a variable in the denominator, whatever value or values for x that you plug in that will give you 0 as a result in your denominator, that's going to be your vertical asymptote. You can also have something called a whole if that factor matches the numerator and the denominator, but we'll look at an example of that in just a moment. Let's do some quick practice in finding vertical asymptotes, which will help us in finding limits of things. So let's say I have this function here. It is a rational function. I've got a variable x in my denominator. Now let's find what's going to break my domain. So it's as simple as taking this thing that's been factored out here, x plus 1, setting it equal to 0, solving for x. So x equals negative 1 is going to be our vertical asymptote. Now let's try this one. Also a rational function. Got a variable in my denominator. So let's set that equal to 0 and see what we find. So once I set that equal to 0, I realized that this is a difference of squares, and that's a quadratic. So I'm going to factor this thing to be x plus 1 and x minus 1, set them both equal to 0, and I get two vertical asymptotes here. One at x equals negative 1 and another at x equals positive 1. In another example, not to leave trig functions out of this, let's find the vertical asymptotes for cotangent of x. What I've got to do here is realize that cotangent of x is the inverse of tangent, so 1 over tan, and tan is sine over cos, so I just flip those. So that means that cotangent is cosine x over sine x, and so sine x is my denominator. Going to set that equal to 0, and what values of x in terms of pi make sine 0 according to the unit circle? That's 0, pi, 2 pi, etc. So I can write it as a repeating x value. So I write it as x equals pi n, where n is an integer, so it's going to repeat every 1, 2, 3, etc. So those are going to be my vertical asymptotes for cotangent of x. All right, so let's take another example where I have yet again a rational function, variable in the denominator, but what I can do here, and hopefully your algebra senses are tingling, we're going to try to factor these and see what happens. And once I factor these guys out, I realize that I have x minus 2 in my numerator and in my denominator. And once I set that equal to 0, I have x equals 2. So you can't have both an intercept and a vertical asymptote at the same place. Those contradict each other. So remember, that creates a hole in your function, not a vertical asymptote. So if you have the same factor on top as on bottom, that's a hole, not a vertical asymptote. So that means the only vertical asymptote I'm going to have is this other factor in the denominator, x plus 2. So when I set it equal to 0, I find that x equals negative 2 is my only vertical asymptote here. And in thinking about infinite limits, I would look at x equals negative 2, and as the function approaches from the left, so that's going to go to negative infinity, and approaching from the right, that's going to go to positive infinity. Now we can't talk about vertical asymptotes without talking about oblique or slant asymptotes as well. So here I have a new function that's a rational function, variable in the denominator, but I know it's going to have an oblique asymptote as well as a vertical asymptote because this power here on the top is 1 greater than the one on the bottom. So although the oblique asymptote doesn't come into effect when I talk about limits or vertical asymptotes, it's still good to know. So I figure out what's going to make my denominator 0 here, and that's at x equals positive 1, so that's going to be my vertical asymptote. And so I'm going to look at how that limit approaches from the left-hand side, so that's going to positive infinity here. And then as it approaches on the right-hand side, that's going to go towards negative infinity there. So always look out for the vertical asymptote. That's going to help you with your limits. All right, and here's some really helpful properties of infinite limits. So let's say that I have two functions, f of x and g of x, and let's say that one of the functions, as it approaches some value c, which is a number, the limit is infinity. And let's say the other one is just some number L. So what all of these rules essentially say that if you add or subtract either of these limits, one that has an infinite limit and one that has a constant limit, you're going to get infinity if you add or subtract those two functions. For product, it's kind of the same idea. You're still going to get infinity as your final limit, but you have to take into account if your limit for the constant number is greater than 0, it's going to be positive infinity. And if your L value, your constant value, is less than 0, it's going to be negative infinity. It's pretty easy to remember that. And then if you have your quotient, so if you have g on top, so that's the one that has the real number limit, and you divide it by the function's limit that approaches infinity, that limit is going to be 0. Let's run through some quick examples of these rules so you can see them in action. So let's take a look at this guy. So our function is 1 plus 1 over x squared as x approaches 0. So we know that that's going to break that denominator here. So this limit is going to be equal to 1, and the other limit that has an x in the denominator is going to approach infinity. And according to the sum rule, that's going to give me infinity as my answer, which is down here. And so if I take another example, it's a little bit more complicated. I've got x squared. So as that approaches 0 from the left, that's going to equal 0. And if I have 1 over x, which we've looked at plenty of times, is approaching 0 from the left as well, that gives you negative infinity. If you're adding those two functions together, you're going to get negative infinity there. Now let's look at an example of a product. So let's say I have the function 3 times cotangent of x. And so I know that the limit of y equals 3 as we approach 0 from the right is going to be 3. And the limit of cotangent of x as we approach 0 from the right is going to be infinity. If I multiply those two together, 3 is greater than 0, so my result is going to be positive infinity. And last but not least, let's look at a quotient rule. So let's say I have my function here. I've got x squared plus 1, which is a limit as it approaches 1 from the left. That's going to be equal to 2. I can look at that graphically and figure that out. So that's going to be my resulting limit that is a constant. So that's a real number. And I'm going to divide it by this limit here, which is the cotangent of pi x as we approach the same number, 1, from the left-hand side. That's actually going to give me negative infinity, which again, I could look at the graph of that, figure that guy out. So I put the real number limit on top divided by the negative infinity on the bottom, and that's going to give me 0, because that's what the rule says. And that's going to do it for this video. Thanks for watching.